In the spring of 1942, Lord Louis Mountbatten, the man responsible for planning the Allied invasion of Europe, asked a question that made every engineer in the room uncomfortable. Could you run a pipeline under the English Channel to pump fuel directly to an invading army? The experts said no. A 6-inch pipe across 70 miles of open sea, tidal currents, and German patrolled waters was simply not possible. The idea was shelved. But then a man walked into the room who had spent years pumping oil through the mountains of Iran, and he saw something nobody else had seen. His name was Arthur Clifford Hartley, and within 7 days of that meeting, a prototype was built. What followed was one of the most extraordinary secret engineering projects of the Second World War. They called it Operation PLUTO, Pipelines Under the Ocean. 21 pipelines laid across the floor of the English Channel. Over 700 nautical miles of pipe manufactured in total. Fuel pumped at 1,500 pounds per square inch. Giant floating drums, 90 feet long and 40 feet across, each one the size of a 9-story building, unspooling pipe into the sea. Pumping stations disguised as ice cream shops and seaside bungalows. Every document classified. Every worker sworn to secrecy. The words pipe and pipeline were forbidden. Everyone called it cable, and it worked eventually, because here is the part that most documentaries leave out. On the 6th of June 1944, the day the Allies stormed the beaches of Normandy, this extraordinary system delivered exactly 0 gallons of fuel. This is the story of the world's first undersea oil pipeline, an engineering marvel that arrived too late, failed repeatedly, and still changed the world. To understand why anyone would even attempt something this insane, you have to understand a single terrifying number. That number, is 60%. During the Allied campaign in Europe, petroleum products accounted for over 60% of all supply tonnage. Not ammunition, not food, not medical equipment, fuel. More than half of everything the Allied armies needed, by weight, was petrol and diesel. A single Sherman tank consumed roughly 1 gallon for every mile it travelled. By the summer of 1944, General Patton's Third Army and General Hodges' First Army were burning through 800,000 gallons of fuel every single day. And that was just 2 armies out of dozens. Now here is the problem. After D-Day, the Allied forces advanced over 300 miles inland from the Normandy beaches. But the major ports were still in German hands. There were no fuel depots, no refineries, no pipelines on the continent. Every drop of petrol had to come from England, across the channel by tanker, then overland by truck. The Americans created something called the Red Ball Express, a massive emergency supply convoy. At its peak, nearly 6,000 trucks, mostly 2.5-ton GMC vehicles, were running around the clock on dedicated one-way highways. They moved 12,500 tons per day. Approximately 75% of the drivers were African American soldiers serving in a segregated army while keeping that army alive. But the Red Ball Express had a devastating flaw, a paradox that no amount of logistics could solve. As the front lines pushed further east, the supply route stretched to nearly 1,000 kilometers round trip. And those trucks ran on fuel, the very fuel they were delivering. At a certain distance, a truck would burn almost as much petrol getting to the front as it carried in its cargo. General Patton's tanks were literally grinding to a halt, not from enemy fire, but from empty fuel tanks. On the 2nd of September 1944, Patton sent a message to Eisenhower that became famous. He said, "My men can eat their belts, but my tanks have got to have gas." This was the crisis that PLUTO was designed to solve, because a pipeline does not consume fuel to deliver fuel. It simply pushes it silently, continuously, invisibly, from one end to the other. So in the spring of 1942, an engineer walked into an office, glanced at a map of the English Channel, and saw something that nobody else had seen. Arthur Clifford Hartley was born in Hull in 1889, the son of a surgeon. He studied engineering at Imperial College London, graduated in 1910, and went to work on the railways. Nothing remarkable so far. Then came the First World War, and Hartley became a pilot. He joined the Royal Flying Corps in August 1916, and there he worked on one of the most delicate problems in aviation: how to fire a machine gun through a spinning propeller without shooting off your own blades. He helped develop the interrupter gear, the synchronization mechanism created by George Constantinescu that allowed bullets to pass between the propeller arcs. An Air Vice Marshal later credited this work with helping to achieve air superiority on the Western Front. Hartley left the war as a major with an OBE, but his real education came after the war. In 1924, he joined the Anglo-Persian Oil Company, later Anglo-Iranian, and later still BP. By 1934, he was their chief engineer. And in Iran, he operated something that nobody in London was thinking about: a 3-inch diameter pipeline that pushed oil at 1,500 pounds per square inch across 40 miles of hilly wilderness, 100,000 imperial gallons a day through a pipe you could almost wrap your hand around. That obscure Iranian pipeline was about to change the course of the war. On the 15th of April, 1942, Hartley visited the offices of the Petroleum Warfare Department in London. On the wall, a large map of the English Channel. Staff engineers had been wrestling with Mountbatten's question for days. Could fuel be piped under the channel? They had been trying to design a conventional 6-inch pipeline. It could not be done. Too heavy, too rigid, too vulnerable to tides and currents. The answer, as far as anyone in that room was concerned, was no. Hartley looked at that map and connected two ideas that had never been connected before. The first, his Iranian experience. You did not need a fat pipe. A small-bore high-pressure line could move enormous volumes of fuel. The second, submarine telegraph cables. Ships had been laying armored cables across ocean floors for nearly a century. The technology for paying out a continuous, flexible line from a moving vessel already existed. His proposal was breathtakingly simple. Take a submarine cable, replace the copper conductor with a hollow lead pipe, armor it with steel tape and wire, lay it from a ship, exactly as you would lay a telegraph cable, then pump fuel through it at high pressure. One line would not be enough, but 20 lines in parallel would deliver a river of petrol. Within days, Geoffrey William Lloyd, the Secretary for Petroleum, carried a sample of pipe directly to Winston Churchill. The response was immediate. Proceed with all speed. 7 days later, engineers at Siemens Brothers in Woolwich produced the first prototype, a hollow submarine cable with a lead pipe heart bound in steel tape and armor wire. But how do you actually build a pipeline that can survive the most dangerous stretch of water in the world? The answer was called HAIS, Hartley, Anglo-Iranian, Siemens, and if you had seen it lying on a factory floor, you would have sworn it was a submarine telegraph cable. That was the entire point. From the inside out, a hollow lead tube with a bore of just 3.05 inches, minimum wall thickness 0.175 inches, coated in petroleum compound, then 2 layers of paper tape, then cotton tape soaked in bitumen, and then the critical structural element, 4 layers of planished mild steel strip tape, each 2 inches wide, wound in a right-hand lay with breaking joints. Over that goes 57 galvanized steel armor wires, each 0.142 inches in diameter, wound in the opposite direction, left-hand lay. The opposing spiral was essential. Without it, the cable would twist and tear itself apart under pressure. Final layers of jute bedding and petroleum compound. Overall outer diameter, roughly 4.5 inches, about the width of a man's fist. The numbers were extraordinary. Working pressure, 1,500 pounds per square inch. But in testing, HAIS cables survived burst pressures of 3,500 to 4,000 psi, even after being bent 6 times around a drum just 6 feet across. Lead sheaths were manufactured in 700-yard lengths, then joined by lead burning into continuous cables of 35 nautical miles each. Production was spread across 7 British manufacturers: Siemens Brothers in Woolwich, Henleys, Callender's, Glover, Pirelli General, Standard Telephones and Cables, and Edison Swan. 4 American factories added another 140 nautical miles. In total, 710 nautical miles of HAIS cable were produced. Over 1,300 kilometres of pipe that looked like telegraph cable, behaved like telegraph cable, and could be laid by a cable ship, but carried fuel. But lead was becoming scarce, so 2 oil field engineers, Bernard Ellis of Burma Oil and H.A. Hammock of Iraq Petroleum, proposed a simpler alternative. They called it Hamel, bare uncoated, mild steel tube, 3.5 inches in diameter, with walls just over 2/10 of an inch thick. Individual 30-foot segments were flash welded into 4,000-foot lengths at a factory in Tilbury. Ellis designed a special broaching tool to scrape metal debris from inside each weld. Hamel was cheaper and faster to produce, but bare steel on a rocky seabed had an expected life of just 6 weeks. It was a disposable pipeline, built to be used and abandoned. Not everything worked the first time. In May 1942, a 120-yard prototype was laid across the River Medway by the post office cable ship CS Alert. It failed after 2 days. The lead core extruded through gaps in the steel tape under pressure. The fix was simple but crucial. Double the steel tape from 2 layers to 4. A second test across the Firth of Clyde succeeded. PLUTO was formally incorporated into the invasion plan. Now they had the pipe. But how do you unroll something this heavy across the bottom of the English Channel? The HAIS cable could be coiled in a ship's tank and laid like a telegraph cable. But the HAMEL steel pipe was rigid. It could not tolerate being twisted lengthwise. You could bend it, but you could not coil it into a hold. So if you wanted to lay 70 miles of steel pipe in a single continuous run, you needed something entirely new. What they built was called the conundrum, and it looked like something from a fever dream. Imagine a cotton bobbin, the kind you would find in a sewing box. Now scale it up until it is 90 feet long and 40 feet across the drum. Add flanges 52 feet in diameter, with teeth around the edge for a chain drive mechanism. Mount the whole thing on hollow steel trunnions, 10¼ inches across, sitting in Timken roller bearings. Now wind up to 70 miles of steel pipe onto it. Fully loaded, a single conundrum displaced 1,600 long tons and sat half submerged in the water like a monstrous floating barrel. 3 ocean-going tugs would tow it across the channel while the drum rotated, paying out pipe to the seabed below. 6 were built by Messrs. Orthostyle at £30,000 each. They were designated HMS Conundrum 1 through 6, because in wartime Britain even a giant bobbin deserved a commission. But the conundrums were only half the story. You also needed ships that could lay HAIS cable from their own tanks, like cable ships, but for fuel. The first was HMS Holdfast, the world's first pipeline-laying vessel. She had been the passenger ship SS London, built in 1921, 1,491 gross tons. Gutted and refitted, she received 2 cable tanks, each 30 feet in diameter, holding 15 statute miles of pipe. Her commander was Henry Treby Heel, a veteran cableman who had previously captained the famous CS Faraday. Later came HMS Latimer and HMS Sancroft, converted Liberty ships nearly 7,000 gross tons each, fitted with 2 50-foot tanks. Each could carry 100 miles of HAIS cable. These were serious vessels for a serious operation. And then, the moment of truth. On the 29th of December 1942, HMS Holdfast sailed from Swansea into the Bristol Channel. The weather was rough. The mission lay 30 miles of 2-inch HAIS cable to Watermouth on the Devon coast and pump fuel through it. During the lay, the Luftwaffe arrived. 2 500-pound bombs landed approximately 100 feet from the Swansea end, a routine raid not targeting PLUTO. The bombs shook the ground. The pipe held. Holdfast completed the lay at 5 knots. Pumps were started at 1,500 psi. Fuel began to flow, 56,000 imperial gallons per day through a single 2-inch line. Continuous, stable, proven. The concept worked. Captain Hutchings took command of Force PLUTO in July 1943. Several ships, over 100 merchant navy officers, and more than 1,000 men. 2 routes were planned, named after Disney characters. Bambi from the Isle of Wight to Cherbourg, roughly 70 miles, and Dumbo from Dungeness to Boulogne, about 31 miles. A cross-Solent connection was codenamed Solo. The pipeline worked. Now they had to hide it. On the Isle of Wight, just off the seafront at Sandown, there was a modest seaside entertainment complex called Brown's. It had a pitch and putt golf course, designed by 3-time British Open champion Sir Henry Cotton, an ice cream factory, a powerhouse, a pavilion, and a Palmerston-era granite fort that overlooked the Solent. In 1942, the entire site was quietly requisitioned. The golf course stayed open. The ice cream factory kept its sign. From the outside, nothing changed. Inside them, 14 industrial pumping units were installed in the fort and the surrounding buildings. The powerhouse held generators. The ice cream factory disguised heavy engineering works. Fuel was piped from concealed storage, through the fort, down the cliff, and into the sea, heading for occupied France. A few miles south, the famous Victorian gorge of Shanklin Chine, a narrow ravine cutting through the cliffs to the beach, concealed the pipeline route from clifftop to esplanade to ocean. The Royal Spa Hotel, already wrecked by a Luftwaffe bomb, was repurposed as a cover for construction. A concrete mixer was hidden inside. Trucks drove in at night, and workers swept the tire tracks clean behind them. On the Kent coast, it was even more elaborate. At Dungeness and Greatstone, on the flat expanse of Romney Marsh, 27 seaside bungalows and houses were gutted and converted into pumping stations. They kept their cheerful names: Happy-Go-Lucky, Sea Breezes, the Douve, reinforced roofs, grass planted on fresh concrete, old beds and broken chairs scattered inside to maintain the illusion of ordinary holiday homes. Components for the Dungeness stations arrived by the Romney, Hythe and Dymchurch Railway, the famous miniature railway with its tiny locomotives, war materials delivered on a tourist attraction. If you were a delivery driver arriving at any PLUTO facility, you had one instruction: ask for Captain Jones. Since the buildings looked like ordinary bungalows or seaside shops, this code phrase was the only way to identify yourself as legitimate personnel. And then there was Dover, the architect Basil Spence, who would later design the new Coventry Cathedral, built a 3-acre fake oil terminal out of scaffolding, fiberboard, and old sewage pipes. It had fake storage tanks, fake pipeline connections, and wind machines that created realistic dust clouds. King George VI visited. Eisenhower visited, Montgomery visited, German reconnaissance aircraft were permitted to overfly at above 33,000 feet, high enough to photograph the terminal, but too high to see that it was made of plywood. Throughout the entire operation, the words pipe and pipeline were strictly forbidden. Every person involved, yet military and civilian, referred to the system as cable. All documents were classified. Records remained sealed for 30 years after the war. And the Germans never found out. Not during construction, not during operation, not until the files were declassified decades later. So the pipes were ready, the pumps were hidden, the ships were converted. On the 6th of June, 1944, the Allies stormed the beaches of Normandy, and Pluto delivered nothing. The original plan was straightforward. Allied forces would capture the port of Cherbourg by D+8, 8 days after the Normandy landings. Pluto pipelines from the Isle of Wight would be operational within days of capture. Fuel would flow. None of that happened. Cherbourg did not fall until the 27th of June, D+21, nearly 2 weeks behind schedule. And when the Allies finally took the port, German demolition teams had destroyed it so thoroughly that it was useless for weeks more. There was nothing to connect a pipeline to. Pluto sat idle through the most desperate phase of the campaign, while Patton's tanks ran dry and the Red Bull Express burned fuel delivering fuel. The world's most ambitious pipeline system delivered exactly 0 gallons. When the Cherbourg route, codenamed Bambi, was finally attempted in August, what followed was not triumph. It was a catalogue of disasters. On the 12th of August, HMS Latimer successfully laid the first HAIS cable, 70 miles from Cherbourg to the Isle of Wight. 10 hours of careful, precise work. The cable reached shore, connection teams moved in, and then a Royal Navy destroyer, one of the escort vessels assigned to protect the operation, dropped its anchor directly onto the cable. The line was destroyed. 2 days later, on the 14th of August, HMS Sancroft laid a second cable. This time the lay was flawless, but during the shore connection at the far end, the cable wrapped itself around the propeller of HMS Algerian. The second line was gone. On the 27th of August, they tried the conundrum approach, the giant floating drum carrying 70 miles of Hamel steel pipe. But the conundrum had been sitting in the water for months, waiting for this moment. And during those months, marine life had taken up residence. 10 tons of barnacles had encrusted the submerged drum, jamming it completely. It would not rotate. After the barnacles were scraped clean, another attempt was made. The pipeline broke, 29 nautical miles out. By late September, one HAIS cable was finally commissioned. Fuel began to trickle, 56,000 gallons per day. It was something. But on the 3rd of October, when engineers increased the pressure from 50 to 70 bars, both the HAIS and the Hamel lines failed simultaneously. The HAIS had a faulty coupling. The Hamel cracked across a sharp edge on the seabed. On the 4th of October, 1944, 4 months after D-Day, Bambi was terminated. Total fuel delivered across the entire Bambi operation, roughly 935,000 gallons over approximately 11 days. For context, Patton's army alone consumed that much in a single day. The project was on the verge of cancellation, but one route remained untried. The Dumbo route was shorter, 31 miles from Dungeness on the Kent coast to Boulogne on the French side, less than half the distance of Bambi. The seabed was better charted, the currents were more predictable, and by October 1944, the engineers of Force Pluto had learned every lesson that Bambi could teach them. On the 10th of October, 6 days after Bambi was terminated, HMS Sancroft sailed from Dungeness, carrying a full load of 3-inch HAIS cable. The lay began in the early hours. The cable paid out smoothly from the ship's 50-foot tanks, sinking to the channel floor at a steady rate. 5 hours later, it was done. 31 miles of pipeline from England to France, laid in a single run without a single fault. On the 26th of October, fuel began to flow. This time, there were no anchors dropped on the cable, no propellers tangling the line, no barnacles, no brakes. The shorter distance, the calmer seabed, and the hard experience of 4 months of failure combined to produce something that actually worked. And once it worked, they scaled it fast. By December, 17 pipelines were operational across the Strait of Dover, 11 HAIS cables, and 6 Hamel steel pipes. Combined output, 1,300 long tons of fuel per day. The HAIS cables on the Dumbo route never broke in service, not once. The engineering that had been proven in the Bristol Channel 2 years earlier held. On the 15th of March, 1945, Dumbo crossed a milestone, 1 million imperial gallons per day. By the 3rd of April, 4,500 long tons per day. The system was not just working, it was accelerating, and the network kept expanding. Pipelines were extended from Boulogne to Calais in November 1944, then further to Antwerp, to Eindhoven, and eventually to Emmerich on the Rhine, inside Germany itself. What had begun as a cross-channel experiment became a fuel distribution network stretching hundreds of miles across liberated Europe. On the 7th of August 1945, 3 months after victory in Europe, the system was shut down. Force PLUTO was disbanded on the 31st of August. By that point, PLUTO had delivered approximately 180 million imperial gallons of fuel, 820 million litres. The commonly cited figure of 172 million represents the total at VE Day. The remaining 8 million flowed through the final weeks of operation. It sounds like a triumph. But was it? 180 million gallons. It is a staggering number. It sounds like a war-winning achievement. And for decades, that is exactly how it was presented. Official histories praised PLUTO as a triumph. Television documentaries called it revolutionary. Museum displays described it as one of the greatest secret operations of the war, but there is a number that most of those accounts leave out. Between D-Day and VE Day, the Allied forces in Europe consumed approximately 5.4 million long tons of petroleum products. PLUTO's cross-channel contribution, the fuel that actually flowed through the undersea pipelines, amounted to roughly 370,000 long tons. That is approximately 8%, not a third, not a quarter, 8%. The rest came by tanker, ships that sailed across the channel, largely unmolested, because by 1944, Allied air and naval superiority was so complete that the feared German threat to channel shipping had simply never materialized. The U-boats and the Luftwaffe, the very dangers PLUTO was designed to bypass, were no longer a serious factor by the time the pipelines became operational. There is a commonly repeated claim that PLUTO delivered 1/3 of all Allied fuel. This appears to conflate the undersea channel pipelines with the entire British government pipeline and storage system, the vast domestic network of overland pipes connecting refineries to ports across the United Kingdom. That system was indeed essential, but it was not PLUTO. The official British historian Derek Peyton Smith delivered perhaps the most damaging assessment. PLUTO, he wrote, contributed nothing to Allied supplies at a time that would have been most valuable. That is, when no regular oil ports were available on the continent. Eisenhower praised PLUTO as second in daring only to the artificial Mulberry harbours. But note his careful wording. He praised its daring, its engineering ambition, not its military effectiveness. The most balanced modern assessment comes from Tim Whittle, writing in a peer-reviewed journal in 2013. His verdict: an engineering triumph that was a logistical disappointment. But this is not the whole picture. PLUTO was never designed to be the sole fuel supply. It was one element of a larger system, and when Dumbo finally hit its stride in early 1945, it freed up tanker tonnage that was desperately needed in the Pacific theater. The official record notes that PLUTO saved very large tanker tonnage badly needed in the East. The total cost was approximately £4.4 million, roughly 243 million in today's money. For 8% of the fuel supply and the world's first undersea oil pipeline, was it worth it? The honest answer is, it depends what you are measuring. But if the military contribution was modest, the legacy was anything but. Here is what PLUTO actually achieved. Not in the war, but after it. Before 1942, no one had ever laid a continuous oil pipeline of significant length across an ocean floor. Telegraph cables, yes, ships had been laying those since the 1850s. Telephone cables, yes, but a pressurized fuel line, armored against tides and currents, and sharp rocks pumping volatile petroleum at over 1,000 pounds per square inch across dozens of miles of open sea. That had never been done. Not once, not anywhere in the world. PLUTO did it first, and the technology it pioneered did not vanish when Force PLUTO was disbanded in August 1945. It evolved, it matured, and it became the foundation of an industry worth hundreds of billions of pounds. The HAIS cable, that ingenious marriage of submarine telegraph technology and high-pressure petroleum engineering, became the direct ancestor of modern composite, flexible pipes. Consider the design principles. A pressurized core, surrounded by structural reinforcement layers, wound in opposing spirals to resist torque, protected by an outer armour of steel wire and waterproof bedding. That is not just a description of HAIS. That is a description of virtually every flexible riser and flowline used on deep-water oil platforms around the world today. The materials have changed. Polymers instead of lead, carbon steel instead of planished tape. But the layered architecture remains fundamentally the same. Hartley's 1942 prototype established a design philosophy that the offshore industry still follows 8 decades later. The Hamel system contributed something equally important: the concept of reel lay installation. Before PLUTO, the idea of winding rigid steel pipe onto a giant floating drum and paying it out from a moving vessel was considered absurd. Pipe was welded together on land or on a lay barge, segment by segment, joint by joint. It was slow, expensive, and dependent on calm weather. The conundrum drums changed that equation entirely. A single conundrum could carry 70 miles of pipe and lay it continuously at speed. The modern reel lay method, now standard practice for installing subsea pipelines worldwide, descends directly from this principle. Today, specialized relay vessels carry thousands of tons of pre-welded pipe on enormous reels and can install kilometres of pipeline in a single day. The efficiency gains are extraordinary, and the concept was born on the English Channel in 1943. When the North Sea oil boom arrived in the 1970s, British engineers drew heavily on PLUTO-era knowledge. This was not coincidence. It was continuity. The seabed conditions, the weather, the tidal forces, the corrosion challenges. They were working in the same waters, facing the same problems, and building on the solutions that Hartley and his colleagues had improvised under wartime pressure 3 decades earlier. The companies that manufactured HAIS and Hamel, Siemens, Callender's, Pirelli, carried their expertise directly into the post-war subsea cable and pipeline industry. By 2016, the United Kingdom sector of the North Sea alone contained over 45,000 kilometres of subsea pipelines and cables. That network, the veins and arteries of Britain's offshore energy industry, owes its origins to a wartime experiment that most people have forgotten. Every barrel of North Sea oil that has ever reached shore has travelled through infrastructure whose fundamental engineering principles were proven in the English Channel during the Second World War. PLUTO was not the only audacious project born from the Petroleum Warfare Department and Combined Operations. These organizations produced a remarkable cluster of unconventional technologies that shared a common philosophy. Take civilian expertise, apply it to an impossible military problem, and build something that nobody thought could work. FIDO, Fog Investigation and Dispersal Operation, burned aviation fuel along runway edges to generate enough heat to clear fog from airfields. It consumed fuel at a staggering rate, but it allowed bombers and fighters to land in zero visibility conditions that would otherwise have been fatal. Over the course of the war, FIDO saved approximately 3,500 aircrew who would have had nowhere to land. The PWD's flame warfare program was even more dramatic. In the dark days of 1940, when German invasion seemed imminent, over 50,000 flame fougasse barrels were placed at 7,000 batteries across southern England, ready to turn roads, beaches, and hedgerows into walls of fire. Geoffrey Lloyd himself had declared the vision. Flame all across Britain, ringing the coasts, spurting from the hedges, and rolling down the hills. They were deadly serious. All three projects shared the same DNA, bold, unconventional solutions championed by Mountbatten's Combined Operations Headquarters and executed by civilian engineers who had never built weapons before. They were amateurs in the best sense of the word, people who solved impossible problems precisely because nobody had told them the rules. But what about the man who started it all? Arthur Clifford Hartley came home from the war with a CBE and the United States Medal of Freedom. The Royal Commission on Awards to Inventors granted him £9,000, tax-free, roughly $500,000 in today's money, for his contribution to PLUTO. Bernard Ellis, who had designed the Hamel pipe, received £5,000. Hartley returned to Anglo-Iranian oil and continued to do what he had always done, build pipelines. But now the engineering world recognized him in a way it never had before. In 1951, his peers elected him president of the Institution of Mechanical Engineers, one of the most prestigious positions in British engineering. He delivered his presidential address on the subject he knew better than anyone: the design, construction, and operation of long-distance pipelines. In 1953, Imperial College London, where he had graduated with a modest third-class honours degree 4 decades earlier, made him an honorary fellow. The young man who had barely scraped through his exams had become one of the most respected engineers in the country. In 1959, he received the Redwood Medal of the Institute of Petroleum, the highest award in the British oil industry. That same year, he was elected president of the Institution of Civil Engineers. It was the crowning honor of a remarkable career, the summit of the profession that he had spent his life serving. He held that office for 3 months. On the 28th of January 1960, Arthur Clifford Hartley passed away at the age of 70. The man who had connected two ideas that nobody else had thought to connect: a small bore pipeline in the Iranian mountains and a telegraph cable on the ocean floor, was gone. His obituary in the ICE proceedings ran to a few paragraphs. The national press barely noticed. He never became famous. There is no statue of Arthur Hartley, no building bears his name, no documentary has been made about his life. If you search for him today, You will find a handful of entries in engineering journals, a brief mention in the IME-CHE archives, and a few paragraphs buried in wartime histories. The man who invented the world's first undersea oil pipeline, a technology that now underpins a global industry worth hundreds of billions, remains almost entirely unknown to the general public. But the physical evidence of what he built is still there, if you know where to look. At Shanklin Chine, on the Isle of Wight, 65 yards of original PLUTO pipe are displayed in the Victorian Gorge, where they were once hidden from German reconnaissance. There is a small museum, a cross-section of the actual HAIS cable, showing every layer, lead, steel, wire, jute, exactly as Hartley specified in 1942. A 10-minute documentary film plays en loop for visitors. Adrian Searle's book, PLUTO, Pipeline Under the Ocean, is available from the gift shop. At Sandown, just along the coast, the old Browns PLUTO powerhouse is now a Grade 2 listed building, maintained by a group of local volunteers who call themselves the Men in Sheds. Inside the Palmerston-era granite fort, which now houses the Isle of Wight Zoo, one of the original 14 pumps has been carefully restored. And the building that once disguised a secret wartime pumping station behind the facade of a seaside ice cream factory is still open for business. It is called Pluto's Cafe. It still sells ice cream. 80 years later, the cover story became the real story. At Dungeness, on the flat expanse of Romney Marsh, several of the disguised PLUTO bungalows survive. Their cheerful wartime names are gone, but the concrete pipeline casings are still visible in the landscape. Silent reminders of the night shifts when workers swept tire tracks from the roads and engineers spoke of cables instead of pipes. And on the floor of the English Channel itself, roughly 10% of the original pipelines remain where they were laid. The other 90% were recovered between 1946 and 1949 in one of the largest salvage operations of the post-war period. 22,000 of 23,000 long tons of lead were salvaged, a material too valuable to leave on the seabed. On the 24th of May, 1945, Winston Churchill told Parliament, "Operation PLUTO is a wholly British achievement and a piece of amphibious engineering skill of which we may well be proud." He was right, but perhaps not in the way he intended. PLUTO was not a simple victory. The pipelines arrived too late for the beaches of Normandy. They failed repeatedly across the long and treacherous route to Cherbourg. They delivered just 8% of the fuel that powered the Allied advance across Europe. By any conventional military measure, they underperformed. But the war ended, and the technology survived. PLUTO gave the world its first undersea oil pipeline. It proved that fuel could be pumped across an ocean floor, reliably, continuously, at industrial scale. It pioneered flexible composite, pipe design, and reel lay installation. It trained a generation of engineers who went on to build the North Sea infrastructure. And it established a principle that the offshore industry has relied upon ever since, that a small-bore, high-pressure, armoured, flexible line can do what rigid engineering cannot. 45,000 kilometres of pipeline now cross the British seabed. Every one of them a descendant of Hartley's idea. It was not a simple triumph. It was something better, an act of British engineering courage that outlasted the war it was built to win.